Well, hello everyone. Thank you for having me here. I'm Vadim Bernshteyn. I was a black hole explorers intern this summer at the CFA. I worked with Drs. Dominic Cheng, Daniel Colombo, and Michael Johnson. And today I want to talk about how we can use polarization modes as probes of horizon scale emission geometry. So first, I think you've all by now seen this picture. This is a polarized image of M87 black hole. This is an amazing achievement of Event Horizon collaboration. But what do we actually see here? Well, there are many things going on at once. There are many effects which uh, can kind of be grouped into two categories. Those which are produced by the plasma effects, what the plasma is doing, such as the synchrotron radiation, the fluid flow, various turbulence and radiation transfer effects, and those determined by the geometry of the situation, the black hole mass, spin, where the plasma is around the black hole, different lensing effects arising from the geometry. And in this project, we're interested in the second group of effects. And specifically, first, we're interested in do lensing effects encode all of the geometry of the situation? And if we look into polarization of the image, can we, by studying lensing, recover the geometric information? So that's kind of the big questions of the project. And we do so by looking at polarization and polarization modes. And the reason we do it is because there is a large amount of previous work which shows that things like beta-2 modes are good tracers of spin. They tell us a lot about the geometry of black holes. They're also useful in studying magnetic field structure and dynamics of the disk. But what we do differently compared to the previous works is that, especially to the work which considers analytic models for emission, we do not assume the equatorial emission, and we impose much weaker priors on the magnetosphere. And our question is, by looking at beta-2 modes, can we still recover useful geometric information even in this more generic situation? The way we describe this more generic situation is using semi-analytic jukebox cone emission model, which is actually an extension of Kerbam model, which we've heard about today. It's an extension to a non-equatorial geometry. Specifically, we assume that all of the emission in the image comes from a few conic surfaces of fluid flow. The full model includes three conic surfaces, which kind of correspond to the thin equatorial disk and the two surfaces of the jets. But because we're doing qualitative study of how beta-2 relates to the geometry, we make our life simpler and only consider one conic surface. As you can see here on the right, it's an example of 4 different models with 4 different cone opening angles. And once we set all of the parameters of the model, we ray trace them using the Krang-Julia package. And the nice thing about Krang is that it allows us to ray trace different subrings of the image separately. So here on the right, I ray traced n equals 0 ring. And these are the intensity images which we get for n equals 0 and the polarized signals. And we are really interested in polarized signal. It has not been explored before for this cone model. And we want to see, by looking at these polarized images, infer something about the geometry. This is a more detailed description of all of the parameters of the model. I think there are 12 of them. I don't want to go into every single one, but the main things we're looking at are the cone opening angle, the black hole spin, the orientation of the magnetic field. The two angles are magnetic field along the surface of the cone and out of the surface of the cone. We fix the observer inclination at 17 degrees, which is reasonable assumption for M87. We don't explore that parameter to make our life simpler. And also, we are interested we want to separate effects of emission at different radii from the black hole. So we, instead of considering the full analytic profile given up to us by the model, we constrain it to a very narrow ring of emission. But we vary where this ring is located as a distance r from the black hole. So these are kind of the parameters we're working with. These are the models we are studying. And the specific quantity we are looking at, as I said before, is the beta-2 mode. It's a well-known quantity EHT science. The formula is shown here. You can think of beta-2 as the second Fourier mode of the polarization pattern on the screen. It's a complex number. It's not, we do not consider it as a function of radius. We collapse all the radial structure into one number. The magnitude of beta-2 shows how symmetric the pattern is. Because our models are very symmetric by nature, the magnitude of beta-2 is always 1. So what we are actually interested in is the argument of beta-2. And here on the right, you can see 4 different cases for the magnetic, for the EVPATX, where the magnitude of beta-2 is 1, but the argument is different because the EVPATX are rotated. And the reason why beta-2 modes are interesting to look at, well, they're nice observables. We can measure them using EHT setup. But what's even more interesting is that with BEX, we expect to be able to measure beta-2 separately for the photon ring. So if we can do that, we're going to get 2 beta-2 modes for n equals 0 and n equals 1. And so the idea of the project is, if we have these 2 modes, how much do they tell us about the geometry of the emission around the black hole? Okay, so this was kind of the setup of the project. We have these models. We have the beta-2 modes we want to look at. First thing we do is we take a random model, which seems reasonable to consider. We fix every parameter except the cone opening angle and spin. We ray trace the models for different theta s and spin, and we ray trace separately n equals 0 and the n equals 1, compute beta-2s, and we plot the results we get. So what we can see here, first, beta-2 modes noticeably change both with spin and theta s. So actually, beta-2 modes have the geometry information in them. We learned something about the geometry by measuring them. What's even more interesting is that the patterns look different for n equals 0 and n equals 1, meaning if we can measure beta-2 for n equals 1, we gain even more information. Maybe we can even constrain things like spin. It gives us hope that it's a useful measurement. Okay, but this was just one specific example, so we want to do it in a more systematic way. So what we do is we generate a grid of values which seem reasonable to us. Again, we ray trace them, n equals 0, n equals 1 separately, and we just see what trends we get in this space of models. First thing we do is once we ray trace them all, we plot the distribution. The x-axis is the argument of beta-2 for n equals 0. The y-axis is the argument of beta-2 for n equals 1. And here's the case where the magnetic fields lie strictly in the surface of the cone. This is the distribution of models we get. And we clearly, the dominant trend here is this main diagonal, which corresponds to beta-2 modes for n equals 0 and n equals 1 being conjugates of each other, which is a cool result. It actually agrees with theory. We expect something like this to hold from the theory of black holes. The location on the diagonal is primarily determined by chi, that is the orientation of magnetic field in the surface of the cone. This is the primary factor that determines where on the diagonal we are. And all the variation we see going off diagonal are geometric effects like spin, cone opening angle, and other parameters. Okay, unfortunately, this nice picture breaks down when we move the magnetic field out of the cone. This is the case is 45 degrees out of the cone and perpendicular to the cone, we see that we go off the diagonal, and the nice dependence on the phi angle is destroyed. On the flip side, if we launch the Beck's mission and we measure the beta-2 modes to be very node conjugates of each other, it means we're dealing with interesting magnetic field lines configurations. So that would be kind of a cool result to get. Okay, so, but the plots I've shown before are kind of overall distributions in the parameter space we have. And we really want to see more specific trends with respect to each of the parameters we have. Unfortunately, it means we have to deal with very multidimensional problem. So we need some nice visual to guide us. The way we decided to visualize information is using the polar plots. Here, the radial coordinate in the plot is the emission radius. The angular coordinate is the argument of beta-2. We fix all other parameters except spin. And when we vary spin, we denote this by color. And n equals 0 and n equals 1 are two different color schemes. So that's a busy plot, but we can see here, so this is basically, the two things are varying here, the emission radius and the spin. And n equals 0 and n equals 1 are for the same model. And we can see that because it's the case where the magnetic fields are along the cone, the primary trend is that one beta-2 is the conjugate of the other. And there is some variation due to spin, as we expected. But now, as we have this visual, we can plot how the situation changes when we vary other parameters, such as the cone opening angle. So we can move from a forward jet to a backward jet, and this is how the situation changes. Note that for n equals 0, everything is pretty much as expected. For a forward jet, beta-2 has very weak dependence on spin because the light didn't really interact with the black hole. And as we move to a backward jet, the light travels around the black hole. It gathers some spin information, and we can see it in the variability here. What's surprising, and what was surprising to us when we first saw it, that for the photon ring, this nice trend doesn't hold. At large emission radii, it looks kind of the same. The forward jet weakly depends on spin, and the backward jet greatly depends on spin. But for smaller radii, there is a flip as we go from forward to a backward jet. And we can even have a configuration like here in the equatorial plane for small emission radii. The photon ring's beta-2 is basically independent of spin, which is interesting. We didn't expect to see that, and it kind of shows that beta-2 dependence on spin in this very generic model is actually not that simple. And the last thing I want to show briefly to give some observational motivation for the talk, we can look at the product of the two beta-2s and to see what measuring of this quantity would give us in regards of the model constraints. The reason we chose this quantity specifically is because it's independent of rotation measure. There's an issue that to measure beta-2s accurately, we need to know how the interstellar medium rotates the polarization pattern. It's called a rotation measure. Determining it can be very hard. So it's nice if we have quantity which is independent of it, and that's just such a quantity we can get using Beck's. And we can see here on the right that the top row is the magnetic field orientation, and we can get very tight constraints on the magnetic field orientation by measuring this quantity with Beck's. As it gets to the second and third row, that is the cone opening angle and spin, there are some constraints we can get out of this, but these are weaker effects compared to the magnetic field, and it's really hard to do. So kind of in conclusion of what I've just said, beta 2 modes encode spin and source geometry information, but in a non-trivial way, in a harder way than, in a more complicated way than we expected. Specifically, bottom ring has complicated dependence of beta 2 on the cone opening angle. And really, the best thing we can measure with beta 2s are the magnetic field structure. To constrain spin and other parameters of the model, we really need stronger assumptions on the magnetosphere. And this is some future work, but instead of going into this, I just wanted to show you this animation showing really the variety of trends beta 2s show with respect to the parameters of the model. Classifying this is really hard. Thank you. Do you have any questions?
Great. Thank you, Vadim. That was really excellent. Looks like Alex is not only clapping, he has his hand up with a question.
Yeah, thank you for this
And
talk.
Andrew too. Yeah.
These are really, really cool plots. I haven't seen these before. The disks with the beta 2 phase for n equals 0 and 1 plotted. Yeah, this type of plot. So one of my main takeaways from this work is that one thing we worry about in imaging is, are we really seeing a near equatorial source, or could it be that we're actually seeing a jet, like a funnel of the jet that lights up, and that would also produce a ring-like image compatible with the HT? And I think one takeaway here is that if you look at beta 2 going from n equals 0 to n equals 1, if it's not a complex conjugation, that could indicate you're not seeing a near equatorial source, but rather a jet funnel. And I think confirming this by looking at the GRMHD simulations where the emission is coming mostly from the funnel of the jet, there's some sane models that do that, would be really useful to know, because that could be a really useful diagnostic of the geometry of the emission region. That's a really cool idea.
That's a great point. Yeah, so definitely the conjugation of the two beta 2s is what we expect to see. And if it's not what we see, it means something is weird or interesting, depending on how you want to phrase it, is going on. I wouldn't say it's necessarily that the emission is not equatorial, because as I've shown here, similar effects can be due to magnetic field lines going basically perpendicular to the fluid flow, which is also interesting, but we will have to do other measurements to decide which situation it is. But yeah, the geometry is definitely imprinted in the beta 2s. We need to figure out the best way to extract it from. Yeah, thank you.
Thank you.
Andrew.
Yeah, I think this is really impressive stuff, and I really like these plots, as Alex said. I think my question is sort of building on this plot. So you explored what happens when you vary I. Have you tried what happens if you vary this assumption that chi equals eta plus 180, or that the in-plane field is parallel to the velocity? Because I've never really fully understood this assumption, because for example, in force-free models, you have the velocity, like the drift velocity, even in plane, perpendicular to the magnetic field. And so this assumption that they're parallel, I think is, yeah, I never really fully understood that. So maybe I misunderstand the angles, but yeah, just interested. Have you considered breaking that assumption? And do you think that would have similar effects on the photon ring polarization?
Thank you. That's a great question. No, actually, this assumption that the fluid flow and the magnetic field lines are coupled is definitely not something we truly expect to hold 100% of the time. So we explored, but we just made this assumption to simplify our parameter space search. We explored some models where this equality doesn't hold and is off by 45 degrees, I think. I don't really remember what the results are. I believe I believe, very qualitatively very similar to these plots. There are some offshoots, but I would say the main results that the magnetic field structure plays the key role, and the this conjugation diagonal is there. I think it was still present. But we definitely need to do a more robust search into what if the fluid flow is not coupled with the magnetic field line. Does that answer your question?
Yeah, I really think it'd be useful to vary that. And I think that's really cool to look at these sort of plots with like VZ models, for example, where you can vary things and on like a more global sense. So yeah, I'd be really interested. I think this is really interesting technology built up. So yeah, thanks.